Welcome to this explainer. When we think of a network router, we usually picture this cold, blinking box of metal in a server room, right? But I want you to imagine it a bit differently. Think of it as a cartographer, a map maker. But here's the kicker. This map maker is blindfolded and locked in a pitch-black room. It desperately wants to help deliver billions of data packets to exactly the right places, but it literally can't do anything until we help it draw the map. And that is exactly what we're doing when we're configuring IPv4 addressing and static routes. We're taking off the blindfold. We're giving the router its eyes and drawing out the paths it needs to do its job.
So let me throw a scenario at you. You just unboxed a shiny, brand new, incredibly expensive enterprise-grade router. You rack it, you plug it into the wall. What does it actually know about the internet, or even your company's network, right out of the box? I mean, what actually happens when it receives its very first piece of data?
The answer is absolutely nothing. Zero. Zilch. An unconfigured router is a total blank slate. If you hand it a packet right now, it doesn't even try to guess where it goes. It literally just throws it in the trash. Out of the box, every single one of its network interfaces is shut down, its routing map is completely empty, and honestly, it doesn't even know what an IP address is yet. It's totally up to us to wake this thing up.
Which brings us right into Section 1, Waking Up Network Interfaces.
Okay, so before we even touch the command line, we really have to ground ourselves in physical reality. We're dealing with dense equipment racks and actual physical copper and fiber cables. If we want our router to push packets out of, say, that gigabit Ethernet 0/0 port, we have to tell the software to actually turn on the electricity to that specific piece of hardware. And here is how we actually make that happen. We hop into global configuration mode, and it's basically a three-step dance. First, we select the interface, so interface G 0/0. Next, we give it an identity with the IP address command, punching in the address and the subnet mask. And third, and seriously, people forget this one all the time, we have to explicitly wake it up. We type no shutdown. That's the command that tells the router, all right, power up this port, start listening, and let's get to work.
But wait, here's where it gets interesting. What if you type all those commands perfectly? No typos, you hit enter, but the interface status still says it's down. You literally just told it no shutdown, so why in the world is it still broken?
Well, this is a perfect example of the difference between your software configuration and the physical real world. When you run a show IP interface brief, you get these status codes. If it says administratively down, that means someone, maybe you, forgot to actually type no shutdown. That's a software block. But if it says down/down, your software config is actually fine, but you've got a physical problem. Maybe the cable is unplugged, or maybe the switch on the other end is completely powered off. You only reach the holy grail of up when both your config and the physical wire are absolutely perfect.
And once we achieve that, we move to Section 2, learning the immediate neighborhood.
See, once we finally get those interfaces to up, something kind of magical happens inside the router's brain. The very second an interface comes fully online with an IP, the router has this epiphany. It automatically writes what we call a connected route into its routing table. It's basically saying, hey, I have a physical cable plugged into subnet A. I know exactly how to deliver traffic there. You didn't have to configure any complex routing for that. It just figured it out because the interface woke up. You'll see this as a C in the routing table. And we're going to contrast that with static routes, which, well, they take a bit of manual labor.
Because here's the thing. Connected routes are awesome for your immediate neighborhood. But what happens when a packet rolls in and the destination IP belongs to a subnet in a completely different city or across the country, a place that definitely isn't physically plugged into our router? Our router knows its own house now, sure, but it doesn't know the highways yet.
So, our map is incomplete. To reach those highways, we have to move to Section 3, Drawing Paths, Static Routes. To build a static route, we use the IP route command. Think of this like hammering a literal road sign into the ground for your router to read. You only need three things. First, the destination subnet ID. That's the town you're trying to reach. Second, the subnet mask. And third, the forwarding instructions. You're either telling the router, hey, shove this packet out of your local serial interface, or you give it a next hop IP address. That basically means hand this packet to the router next door at this specific IP address, and let them worry about the rest of the trip.
And when you type show IP route, you finally get to see the map you're building. Now, I know it can look a bit like the Matrix at first glance, but let's decode it. On the left, you've got your route codes. C is for connected. S means static.
That's the road sign you just built. Then you'll see the destination subnet. Next to that, you've got these numbers in brackets, like a 1 and a 0. That first number, that's the administrative distance, which is basically how much the router trusts that route. And finally, the via section tells you exactly where to send the traffic next. Your map is officially taking shape.
But let me throw another wrench in the gears. Imagine you run a post office. You know all the local zip codes. But what do you do if you get a letter addressed to a zip code you've literally never seen before? In networking, if a router gets a packet for an unknown destination, its default instinct is to just drop it in the trash. But obviously, we can't let it just drop internet traffic willy-nilly.
So the elegant fix for this is the static default route. We configure IP route 0.0.0.0 with a mask of all zeros, usually pointing straight to our internet provider's router. This is known as the gateway of last resort. We're essentially telling our router, listen, if you check your whole map and you have absolutely no clue where this packet goes, just hand it to this guy. He probably knows. It's this massive catch-all bucket that keeps the internet flowing smoothly.
But as we all know, things break. Which brings us to Section 4, the ultimate backup plan.
Here is a hard truth about networking. Imagine you drew this beautiful static route, pointing all your company's highly critical data over a super fast fiber link. But then, a construction crew outside accidentally slices right through that fiber cable with a backhoe. Boom, your primary path is completely dead. If you don't have a backup plan already in place, your network goes down instantly and your phone is going to start ringing off the hook.
Enter the floating static route. This is such a brilliant little trick. Remember how we talked about administrative distance being the router's trust level? Well, a standard static route has an AD of 1. It's highly trusted. But if we create a second static route going over a slower backup connection, we can actually manually tweak its AD to be much higher, say 130. Because 130 is worse than 1, the router completely hides this backup route. It literally floats beneath the surface of the routing table. But the exact second that fiber cable gets cut, the primary route vanishes and boom, the floating static route surfaces, injects itself into the map, and saves the day without you ever having to lift a finger.
But what happens when your map just isn't working right from the get-go? Let's talk about Section 5, troubleshooting broken routing maps.
Look, before you spend 3 hours glaring at iproute commands on your screen, you gotta check your physical layer first. Are the indicator lights actually blinking? Is the interface showing up? You simply cannot route packets over a severed cable. Never forget that all this fancy abstract software relies entirely on the physical hardware working correctly. Okay, but let's say the cables are perfect, yet your static route still refuses to show up in the routing table. Time for a practical mental checklist, the rule of 3. First up, did you mess up the subnet math when you typed the command? A single typo in the mask ruins the whole thing. Second, is your next hop IP actually reachable? The router isn't going to add your static route if it can't even talk to the neighbor you're pointing to. And third, is your outgoing interface down? If the port is shut off, the route is useless, so the router just hides it. Now, when you're trying to prove your routes actually work, your go-to tool is ping. But here's the catch. A standard ping only tests if you can get to the destination. What if the remote router doesn't know how to get back to you? That is where the extended ping becomes your ultimate detective tool. By forcing the ping to originate from a specific source IP on your local network, you aren't just testing if the packet arrives. You're testing if the remote router's map knows exactly how to send the reply back to your specific subnet. It verifies the entire round-trip logic.
So, we've woken up the interfaces, we've discovered our immediate neighbors, we've drawn out static paths, and we've even built sneaky floating backup routes. Our cartographer's journey for configuring IPv4 addressing and static routes is totally complete. But I want to leave you with one final thought. Static routes are amazing when you only manage 5 or 10 routers. But what if you work at a massive global enterprise with thousands of routers, and the physical topology is changing every single second? You literally couldn't redraw the map fast enough by hand. So, how do routers teach themselves the map dynamically? Well, that is a massive, fascinating puzzle for next time. Thanks for joining me on this explainer.